Good day and welcome to Big Bad Tech. I'm your instructor Jim Pytel. Today's topic of discussion is balanced Y-configured loads. Our objective is to examine balanced Y-configured loads in three-phase AC circuit analysis scenarios. This lecture operates under the presumption the viewer has more than a passing familiarity with three-phase AC, as illustrated in the Introduction to Three-Phase AC lecture, available at the Big Bad Tech channel. If you haven't watched this lecture yet, or only dimly recall its contents, please take the time to do so now. Three-phase AC circuit analysis is often preceded by the foreboding statement, "Abandon all hope, ye who enter here." This needn't be the case, especially for balanced load configurations, the topic of today's lecture. If you're reasonably competent in performing single-phase AC circuit analysis, this should be a skill well within your reach. This being said, you need to have a level of organization and visualization skills to survive a meeting engagement with three-phase AC circuits with some level of dignity intact. Let's discuss some general tactics for three-phase AC circuit analysis before we begin our discussion of balanced Y-configured loads. Prior to beginning any three-phase AC circuit analysis, balanced or unbalanced, Y or delta configuration, I typically ask myself a series of simple questions starting with, what voltage does a load in this particular system see? Does a load see the line-to-neutral differential or the line-to-line differential? After satisfying this first question, I then ask myself the simple follow-up. What current does a load in this particular system experience? Does a load directly experience full line current, or does it experience only a portion of line current? The answers to these two simple questions are of tremendous benefit to any three-phase AC circuit analysis scenario. Once these initial questions are answered, the active analysis is merely application of single-phase AC circuit analysis principles, like Ohm's law and the power equations, techniques you've had ample exposure with by now. Even the dreaded unbalanced three-wire Y configuration, a monster of fearsome repute, can be rendered into a tame and docile beast that sits, stays, and rolls over on command with a little advanced planning and forethought. As I hope to demonstrate, three-phase AC circuit analysis isn't nearly as hard as you might expect, and even those scenarios that as a whole may refuse to bend to your will can easily be broken into three easily manageable portions using the superposition theorem. If you recall in the aforementioned lecture, we examined Y and delta configuration of three-phase AC sources and compared and contrasted line-to-neutral voltages and line-to-line voltages. Consider a four-wire Y configuration composed of three sinusoidal AC voltage sources, each with an effective value of 120 volts, offset from each other by a relative 120 degrees. Between L1 and conjoined neutral terminal N, there is a differential of 120 volts at an angle of 0 degrees. Similarly, between L2 and N, there is a differential of 120 volts at an angle of negative 120 degrees. And finally, between L3 and N, there is a differential of 120 volts at an angle of 120 degrees. The line-to-line differentials necessitate some minor calculations. Using phasors, L1 to L2 is 208 volts at an angle of 30 degrees. L2 to L3 is 208 volts at an angle of negative 90 degrees. And L3 to L1 is 208 volts at an angle of 150 degrees. If we didn't want to use phasors and wanted to use a shortcut, we could say each line-to-line differential is square root 3, or roughly 1.73 times larger, and offset by 30 degrees. Either method, phasor math or the shortcut, yields the same result. We can also center these resultant phasors on the origin of our original phasor diagram. Again, note both the line-to-neutral and line-to-line differentials each exhibit a relative phase shift of 120 degrees from each other. 120 degrees separates L1 from L2, L2 from L3, and L3 from L1. Similarly, 120 degrees separates L1 L2 from L2 L3, L2 L3 from L3 L1, and L3 L1 from L1 L2. This phasor diagram assumes L1 is our reference at 0 degrees. If we wanted to, we could also reference this whole system with respect to the line-to-line differentials. Assuming we choose L1, L2 as our reference, L1, L2 is 208 volts at an angle of 0 degrees. L2, L3 is 208 volts at an angle of negative 120 degrees, and L3, L1 is 208 volts at an angle of 120 degrees. Given L1, L2 is now assumed to be our new reference, L1 is 120 volts at an angle of negative 30 degrees. L2 is 120 volts at an angle of negative 150 degrees, and L3 is 120 volts at an angle of 90 degrees. Either phasor diagram is correct as long as the user is aware of which reference is being employed, either one of the line to neutral voltages or one of the line to line voltages. You need to be aware that the phasor diagram on the right is identical to the one on the left, only it's been shifted 30 degrees clockwise, or negative 30 degrees to account for L1, L2 being employed as the reference. Similarly, the phasor diagram on the left is identical to the one on the right, only it's been shifted 30 degrees counterclockwise, or positive 30 degrees to account for L1 being employed as the reference. More to the point, you should realize that this is a dual voltage three-phase AC system. Load elements using the line to neutral connection would experience the smaller 120 volt line to neutral differential, whereas load elements using the line to line connections would experience the larger 208 volt line to line differential. This is pretty cool and the focus of our introductory exploration today. Let's simplify the three-phase AC source as solely the L1, L2, L3, and neutral lines. Using this simplification, we're not aware of internal details, however, we are aware of both line to neutral and line-to-line differentials. If we didn't use the neutral connection, or somehow restricted access to it, we'd still be aware of the line-to-line differentials. Let's now take a look at how various load configurations interact with these different voltage levels. If you recall, a Y configuration is an arrangement of three load impedances where each branch impedance radiates from a central node forming the shape of a Y. Y-configured loads can interact with three-phase AC sources in one of two related manners. A four-wire Y configuration directly connects the pooled central connection of the load to the end connection of the three-phase AC source, whereas a three-wire Y configuration does not. The general diagram for both these Y configurations shows impedance element Z1 is directly connected to node A, impedance element Z2 is connected to node B, and impedance element Z3 is connected to node C. A delta configuration, in contrast, is a continuous looped arrangement of three load impedances forming the shape of a triangle. Similar to the three-wire Y configuration, a delta configuration does not make use of the end connection. In this general use diagram, impedance element ZAB goes from node A to node B. Impedance element ZBC goes from node B to node C, and impedance element ZCA goes from node C to node A. I will admit delta connections are a little confusing, and to lessen the confusion, I encourage you to just pick a direction and go with it. In this case, I go from A to B, B to C, and C back to A. These diagrams make two very important facts quite clear. A four-wire Y configuration makes use of the smaller line to neutral voltage from a node of interest to the end connection, whereas the delta configuration makes use of the larger line to line voltage from node to node. We'll examine the particulars of three-wire Y configurations in a moment. Allow me a moment to expound upon these important observations for those that aren't immediately seeing this. Let's take a look at the four-wire Y configuration first. For convenience sake, let's assume L1 is our reference. As such, L1 has a phase shift of 0 degrees, L2 has a phase shift of negative 120 degrees, and L3 has a phase shift of 120 degrees. Using L1 as our reference, the line-to-line differentials are offset by a relative 30 degrees. L1, L2 has a phase shift of 30 degrees, L2, L3 has a phase shift of negative 90 degrees, and L3, L1 has a phase shift of 150 degrees. The differential L1 applied at node A and conjoined terminal N establishes a differential of 120 volts at an angle of 0 degrees. load impedance Z1 goes from node A to node N. It makes sense that the voltage across the load impedance Z1 is 120 volts at an angle of 0 degrees. Similarly, L2 between node B and conjoined neutral terminal N establishes a differential of 120 volts at an angle of negative 120 degrees. Load impedance Z2 goes from node B to node N. It makes sense that the voltage across load impedance Z2 is therefore 120 volts at an angle of negative 120 degrees. Finally, L3 establishes a differential of 120 volts at an angle of 120 degrees between node C and node N. Load impedance Z3 goes from node C to node N. It makes sense that the voltage across load impedance Z3 is therefore 120 volts at an angle of 120 degrees. In summary, load impedance in a 4-wire Y configuration experience the line to neutral differential. Let's now take a look at the 3-wire delta configuration. For convenience sake, let's assume L1, L2 is our reference. As such, L1, L2 has a phase shift of 0 degrees. L2, L3 has a phase shift of negative 120 degrees, and L3, L1 has a phase shift of 120 degrees. Using this particular reference offsets the line to neutral differentials by a relative 30 degrees. L1 has a phase shift of negative 30 degrees, L2 has a phase shift of negative 150 degrees, and L3 has a phase shift of 90 degrees. Between lines L1 and L2, connected to nodes A and B, there is a differential of 208 volts at an angle of 0 degrees. Load impedance ZAB goes from node A to node B. It makes sense that the voltage across load impedance ZAB is 208 volts at an angle of 0 degrees. Similarly, between lines L2 and L3, connected to nodes B and C, there is a differential of 208 volts at an angle of negative 120 degrees. Load impedance BC goes from node B to node C. It makes sense that the voltage across load impedance ZBC is 208 volts at an angle of negative 120 degrees. Finally, between lines L3 and L1, connected to nodes C and A, there is a differential of 208 volts at an angle of 120 degrees. Load impedance ZCA goes from node C to node A. It makes sense that the voltage across load impedance ZCA is 208 volts at an angle of 120 degrees. In summary, loads in a delta configuration experience the line-to-line differential. Again, load impedances in a 4-wire Y configuration experience the smaller line-to-neutral differential, whereas load impedances in a 3-wire delta configuration experience the larger line-to-line differential. You need to pause the lecture and dig this on every level that I do before you move on, because it's about to get real confusing real quick. Let's talk about current. Whereas voltage is pretty easy to describe using a point-to-point differential, current flow through 3-phase AC circuits takes a little bit more foresight and planning. Consider current flow in a 4-wire Y configuration. Current in line L1 must travel through load impedance Z1. Current in line L2 must travel through load impedance Z2. Finally, current in line L3 must travel through load impedance Z3. It can be said that line current equals load current for a 4-wire Y configuration. The 4th wire in a 4-wire Y configuration serves as a return path for any imbalanced current between the different phases. Kirchoff's current law, applied to the central node, implies that current in the N line equals I1 plus I2 plus I3. More on this in a moment. The important takeaway being that line current equals load current for a 4-wire Y configuration. 3 ammeters placed in series on the 3 lines could easily measure both current in that particular line and current in that particular branch impedance because they are one and the same. Again, line current equals load current for Y-configured impedances. If only current flow through delta configurations could be so easy. So we don't lose ourselves in the forest, let's leave a trail of breadcrumbs so we can find our way back by incorporating some ammeters in the following fashion. Ammeter 1 measures line 1 current from the source to node A. Assumed direction of travel is left to right. Ammeter 2 measures line 2 current from the source to node B. Assumed direction of travel is left to right. Finally, ammeter 3 measures line 3 current from the source to node C. Assumed direction of travel is left to right. 3 additional ammeters are then used to measure current through the load impedances. Again, just pick a direction and go with it. A to B, B to C, C back to A. Ammeter AB measures current through impedance element ZAB. Assumed direction of travel is A to B. Ammeter BC measures current through impedance element ZBC. Assumed direction of travel is B to C. Finally, ammeter CA measures current through impedance element ZCA. Assumed direction of travel is C to A. Given these assumed directions of travel for line and load currents, let's apply Kirchoff's current law to each of the nodes forming the delta configuration. Consider node A. Both I1 and ICA are incoming current paths, whereas IAB is an outgoing current path. An application of Kirchoff's current law demonstrates that I1 equals IAB minus ICA. Similarly, consider node B. Both I2 and IAB are incoming current paths, whereas IBC is an outgoing current path. An application of Kirchoff's current law demonstrates that I2 equals IBC minus IAB. Finally, consider node C. Both I3 and IBC are incoming current paths, where ICA is an outgoing current path. An application of Kirchoff's current law demonstrates that I3 equals ICA minus IBC. Consider this larger picture. Current IAB travels through the ammeter on line 1 left to right, through load impedance ZAB from A to B, and through the ammeter on line 2 right to left. Similarly, current IBC travels through the ammeter on line 2 left to right, through load impedance ZBC from B to C, and through the ammeter on line 3 right to left. Finally, current ICA travels through the ammeter on line 3 left to right, through load impedance ZCA from C to A, and through the ammeter on line 1 right to left. You may wish to rewind that last part. The important takeaway being that unlike our observations of Y configurations, line current does not equal load current for 3-wire delta configurations. Line current is in effect the combination of 2 currents exhibiting a relative phase shift between each other coming and going. Given our previous experience with the line-to-line differentials, is it any wonder that line current for delta configurations will be larger than load current and exhibit a phase-shifted offset? It shouldn't be. Despite the subtractive nature of the Kirchoff's current law equation for each node, accounting for phase shift, line current is always greater than load current for delta configurations. We'll examine the specifics of delta-configured loads in later lectures. For now, I just need you to burn these general facts into your long-term memory, because believe me, you'll be seeing them again and again and again. With respect to voltage distribution, load impedances in 4-wire Y configurations experience the smaller line-to-neutral voltage differential, whereas load impedances in a 3-wire delta configuration experience the larger line-to-line differential. With respect to current flow, current in a particular line is equal to the current through a particular load for a 4-wire Y configuration, whereas line current for a delta configured load is greater than load current. Like I said, we'll examine delta configurations in greater detail in the very near future. For now, let's put these observations aside and deal with only balanced Y configured loads. It goes without stating that Y configurations look like Ys. This being said, Ys take up a lot of space and it's sometimes easier to draw them as such. You'll note this diagram is functionally equivalent to a Y configuration. Load impedance Z1 between node A and end has a magnitude of 365 ohms at an angle of 28 degrees. Similarly, load impedance Z2 between node B and node N also has a magnitude of 365 ohms at an angle of 28 degrees. Finally, load impedance Z3 between node C and node N also has a magnitude of 365 ohms at an angle of 28 degrees. This is the definition of a balanced load. All impedances constituting the Y configuration have not only the same magnitude, but also the same angle. Z1 equals Z2 equals Z3. Source L1 establishes a differential of 120 volts at an angle of 0 degrees between node A and node N. Load impedance Z1 goes from node A to node N. It makes sense that the voltage across load impedance Z1 is 120 volts at an angle of 0 degrees. Similarly, source L2 establishes a differential of 120 volts at an angle of negative 120 degrees between node B and node N. Load impedance Z2 goes from node B to node N. It makes sense that the voltage across load impedance Z2 is therefore 120 volts at an angle of negative 120 degrees. Finally, source L3 establishes a differential of 120 volts at an angle of 120 degrees between node C and node N. Load impedance Z3 goes from node C to node N. It makes sense that the voltage across load impedance Z3 is therefore 120 volts at an angle of 120 degrees. Current in line 1 travels through load impedance Z1 and returns via the neutral connection. Similarly, current in line 2 travels through load impedance Z2 and returns via the neutral connection. Finally, current in line 3 travels through load impedance Z3 and returns via the neutral connection. It can be said that line current equals load current. A Kirchoff's current law analysis of IN suggests that IN equals I1 plus I2 plus I3. In summary, each impedance element in this balanced 4-wire Y configuration experiences a smaller line to neutral voltage, and each load impedance experiences the line current. These are the most fundamental aspects of 4-wire Y configurations. Before we dive into the specifics of this analysis, allow me to make this bold prediction about this balanced circuit. Given each branch impedance is identical, and each branch impedance experiences the same voltage magnitude, my understanding of Ohm's law tells me that each branch impedance will experience the same current magnitude, relative phase shift, apparent, real, and reactive power. Let's see how well these predictions hold up to analysis.